So now we are going to move on to the second and the most popular method of finding the point estimators, that is method of maximum likelihood. In this case, let us first understand the setup and then we will address different examples. Here, if you have a random sample of size n from a population having the PDF or PMF of this form, where theta is the unknown parameter and you want to estimate that parameter, in such a case, the corresponding realized values will be denoted by these xi's, small xi's. Okay. Now, the likelihood function of the sample would be a function of parameter theta, which is nothing but probability that capital X1 takes the value small x1, right? And so on up till the last one. Okay. And since these are independent, you can write them as the product of their individual densities over here. And this is nothing but you can write where xi's, f of xi given theta, where I is from 1 to n. Okay, so you see that the likelihood function is a function of the parameter. It is not the function of the random sample, because here the sample has already been observed. So you are substituting it with the realized values. Okay, so here you see that is why you have small xi's. You do not keep the random variable. Okay. And the maximum likelihood estimator of the parameter theta is that value of theta which maximizes this likelihood function. And it is intuitively correct also, because we want the estimator to be such that it will be that value of theta which maximizes the chances or likelihood of getting that particular sample. Okay, so in simple words, what you can understand about this likelihood function or MLE is basically, once you have observed the sample, you have obtained it. Now you want to see which parameter is most likely to have given rise to that particular sample, which parameter caused that sample to occur. Okay, so we are basically finding the maximum likelihood estimator or the value of theta which is going to maximize your likelihood function. And in this case, here we will consider different examples. So first of all, we will consider the discrete case where you have a single observation which follows your binomial distribution with parameters n and p, and only one observation is known to you, and you know that n is the number of trials in binomial distribution. This is going to be either 2 or 3, and the probability, that is p, is either 1 by 2 or 1 by 3, and in that case you have to find the MLE for this. The other cases could be, suppose from here, instead of using binomial, we can have Bernoulli P or uniform zero theta, which we have considered earlier also for method of moment. So we will see that do we have any difference from the method of moment estimator and MLEs, or do both of them give the same result? And also your normal distribution. So these are the examples that we are going to consider. So let us address them one by one. So now we are going to talk about the maximum likelihood estimator. Okay. The first example in our case is that if x follows binomial with parameters n and p, where n can take value 2 or 3 and p can take value either 1 by 2 or 1 by 3. And in that case, we need to estimate the parameters n and p. Now, let us first recall what is the binomial distribution. Binomial distribution basically says that if you have this random variable over here, then this is basically the number of success in n independent Bernoulli trials. So what do we mean by Bernoulli trials? Basically, it means that there are only going to be 2 possible outcomes. That is, all the possible outcomes can be only categorized as success or failure. And in that case, you will repeat the experiment n times, and in that you are going to observe how many success you have obtained. Now the PMF, if you can recall, PMF for binomial is probability that x is equal to x, that it is going to observe these many number of success, it will be n choose x, p raised to the power x, q raised to the power n minus x. Here x takes value from 0, 1, 2 and so on. And it makes sense because here why do we have x going from 0, 1 to n? Because the number of success can be 0 also. Okay, you may get a success or you may not even get them, right? There can be only one success, and likewise it can have at max n success because n is the number of trials, so it will have that many number of success only. Okay, so here in our question it is given that n is 2 or 3. Okay, so let us first of all make this table. So in this case x can take value. What are the values that x can take? X can go from 0, 1, 2 and 3 because 3 is the maximum number of trials. Okay, now what are the possible combinations? N can be 2, 1, probability can be 1 by 2, n can be 2, and this can happen with probability. Likewise you will have 4 different combinations, so let us write those. So 2, 1 by 2, next is 2 and 1 by 3, then you have 3, 1 by 2 and 3, 1 by 3, and finally you will have the maximum probability corresponding to them. Okay, now you have to substitute for each of these because the formula is probability that x is equal to x. Now x can go from 0, 1 to 3 because the number of trials can be either 2 or 3. So we would like to have it till 3 and see. So probability that x is equal to 0. So in this case, let us target this one, first observation over here. The formula is n. So the number of trials in this case in the first situation is, so the number of trials is 2. So 2 choose 0. What is p in this case? P is 1 by 2 raised to the power 0, and again 1 by 2 raised to the power 2. So this would basically mean that this is probability is 1 by 4. So we can write here 1 by 4, right? Likewise, when probability that x is equal to 1, you would have 2 choose 1, 1 by 2 raised to the power 1 and 1 by 2 raised to the power 1. Again, this would be 1 by 2. So let us write this value over here. And if you keep on doing it, for probability x is equal to 2, you would find probability x is equal to 3, you would find. See, what will happen is that when x is equal to 3, it means for this particular case over here, n is 2, the number of trials is 2. So you cannot go beyond that. You cannot have the number of success more than the number of trials. So in that case, this probability would be 0 in this case. Likewise for this case also, here the number of trials is 2 and we are looking at the probability that the number of success is 3, and that is not going to happen. So you have this probability at 0. Now in this case, you will have certain probability because here the number of trials is 3 and the number of success is also 3. So it means that all 3 trials have led up to your success. All 3 trials have given success to you. So it means that it will have certain probability. So I have calculated these values. So I can just write these here. So you can cross check them. So 1 by 4, here it would be 4 by 9. This also comes out as 4 by 9, 1 by 9. So in this case, what will happen? So here you will have probability x is equal to 0 would be there, right? Here for this case, if you see 2 choose 0. So here the probability would be 1 by 3. Instead of 1 by 2, you would write 1 by 3, and here also 1 by 3 raised to the power 2. So that is why you have 4 by 9, 4 by 9, 1 by 9, 0. Here you will have 1 by 8, 3 by 8 and 3 by 8 again, and this one would be 1 by 8. So you will have 1 by 8. Likewise, when you have 3, 1 by 3, so this would be 8 by 27, you would have 12 by 27 and 6 by 27 and finally 1 by 27. Now if you look at x is equal to 0, this particular column over here, so let me use red color. If x is equal to 0, what is the maximum probability in all four of these? It is basically 4 by 9. So here you will write 4 by 9 is the maximum probability among these four. So it means that this possible combination, when n is 2 and probability is 1 by 3, then it is most likely that you will have x is equal to 0. Or you can say that in other words, when you have observed x as 0, it means that once you have observed the sample, now which parameters are more likely to have given rise to this? It is n is 2 and p is 1 by 3. So here 4 by 9. Next case, if you see for x is equal to 1, 1 by 2 is the maximum one. Likewise here it will be 3 by 8 and finally you will have 1 by 8. So if you want to summarize this information, here you could write that what are your estimates? So you are writing n hat p hat, and since we wanted to show that this is based upon x, so here depending upon the value of x, so x can be 0, x can be 1, x can be 2, or it can be x is equal to 3. Now when x is 0, which is the maximum probability? It is 4 by 9 and it is given by n as 2 and p as 1 by 3. So this one would be 2 and 1 by 3. Okay. So here note that you don't have to write the probabilities that you have obtained. You have to find the estimate for the population parameters. It means you have to come up with the values for n and p. Okay, and that basically is coming from 2 and 1 by 3. Now 1 by 2 corresponds to this situation over here, right? 2 and 1 by 2. So n is 2, probability is 1 by 2. Likewise, when x is 2, right? So when x is 2, let us check, it is 3 by 8, which is given by 3, 1 by 2, and finally this one is also given by the same thing. So n is 3 and p is again 1 by 2, and this is also 3, 1 by 2. Okay. Yeah. So this is your MLE for the parameters n and p. Okay. So this is for the situation when n is 2 or 3, you doubt this, and p basically is 1 by 2 or 1 by 3. So maybe now you could try at home with n as 3 or 4 and p as 1 by 3 or 1 by 4. So in this case also you will have different situations, you will have different xi's. So you can see that x in this case will go from 0, 1, 2, 3 and maximum 4, right? And you will have different combinations of n and p, 3, 1 by 3, then you will have 3, 1 by 4, 4, 1 by 3, 4, 1 by 4, and you can note down the maximum probability here. Okay, so you can fill these and finally you will have your answer. So in some cases you will have probability as 0 because n is 3 over here and you are looking at number of success as 4. So this would be 0, this would be 0. Here you would get certain values. Okay, so this is how you deal with your maximum likelihood estimator when you have a single observation and the information that is given to you is of this form. Now let us see what happens when you have, instead of a random variable, you will have a random sample. Then how do we deal with this? How do we find the maximum likelihood estimator? So now we are going to consider our second example, which says that you are taking a random sample from Bernoulli distribution with parameter p. And we know that Bernoulli is a special case of your binomial. Okay. So here, if you recall, the PMF for this is probability that x is equal to x is basically p raised to power x q raised to the power 1 minus x, and here x can only be 0 and 1. Why it can be 0 and 1? Because in Bernoulli what happens is that you are going to take only a single trial of the experiment. Okay, so single trial, and there are only two possible outcomes. So single trial, it means that either you can obtain the success, right, or you may not even obtain a success. So in this case, so x can be 0, it means no success, and if you obtain the success, it will be 1. Okay, so now when you consider for a sample, this is basically saying that xi takes value small xi, this would be probability p raised to power xi, q raised to power 1 minus xi. Now when we have to find the likelihood function, here the parameter is p, what we do is that we have, since these are a random sample, so it means they are independent and identically distributed. So this one would be in this way, and so on up till probability that capital Xn takes this, right? Now you can substitute the values. In this, if you see, when you keep I as 1, so you will have p raised to the power x1, q raised to the power 1 minus x1. Next one would be p raised to the power x2, q raised to the power 1 minus x2, and so on, p raised to the power xn, q raised to the power 1 minus xn. So you can now look at the powers over here, p, so x1 plus x2 up so on up till xn, q raised to the power, so there are n such ones, so n minus x1 plus x2 plus and so on up till xn. So this one would be p raised to the power summation xi, q raised to the power n minus summation xi. Okay, so you have the likelihood function. Now you want to maximize it, and we know that how do we maximize it? Maximize a function, we differentiate it and equate it to 0. Now in maximizing the likelihood function L p, this is equivalent to if I want to maximize this is equivalent to maximizing the log of this. Okay, because this over here is a monotonically increasing function, right? So both of them would give you the same result. So here let us take the log of this. So log of LP would be summation xi log p plus n minus summation xi log q. Instead of that, you can write 1 minus p also. Now when you differentiate it with respect to p, what will you have? Summation xi by p plus n minus summation xi over 1 minus p. Okay, so here a minus sign would come in between. So this would come, and you can further simplify this. So this would be summation xi times 1 minus p minus n minus summation xi times p divided by p into 1 minus p. Here some terms will cancel out. So what are those? So you will have summation xi minus p times summation xi minus np, okay, minus plus p times summation xi divided by p into 1 minus p. So this and this would cancel out. So you will have summation xi minus np divided by p over 1 minus p. So now if you equate it to 0, what you have is that summation xi minus np would be 0, which basically implies that p over here would be summation xi by n. So here n, we are considering that it is known to us. So here p hat would be this. So you can say that p hat is nothing but the estimator. If you say, it would be x bar. So if you say maximum likelihood estimator, it is x bar. If you want to say maximum likelihood estimate, it would be this sample mean which you have obtained over here, right? So this would be till the point that you know that, okay, this is going to be my estimator. But once you have observed the sample, you will substitute the values and then you would say that this is your estimate. Okay. So for Bernoulli case, we have X bar as your maximum likelihood estimator. Okay. Sample mean. So these were the two discrete cases. Now let us consider the third case when you have a random sample coming from uniform 0 theta. Okay. So when you have uniform 0 theta, let us see, is it going to be different or same as the one that you obtained from method of moments? So if you recall, in the method of moments, what you had is theta had came out as twice of the sample mean. Okay. Now let us see what will be your theta hat in this case for MLE. So this was from method of moments and here it would be for MLE. So let us see what it will be. So first of all, you know that the PDF for your uniform distribution is 1 over theta if x takes value between 0 and theta and it is 0 otherwise, right? In this case, what will be the likelihood function? So likelihood function will be product of these fxi's for different xi's, parameter theta, right? So this one would be 1 over theta. Everywhere you will have 1 by theta into 1 by theta and so on, right? So it will be 1 over theta raised to the power n if 0 and all the xi's, basically x1 can also be between, see, x1 would be between 0 to theta, x2 would also be between 0 to theta and so on up till xn. So instead of that, what you can write is so instead of that, you can write that all xi's are here, right? You can just say all xi's are between 0 to theta, or in other case, it would be 0, right? So this is your likelihood function. Now what you have is, let us try to see what is this part over here. Now since all the xi's are between 0 to theta, it means that if I order them, it will be in this way. The first order statistic, then second order would come, then it will go on up till the maximum one, right? Because we know that if you have x1, x2, xn as the observations, and if you arrange them in an increasing order, we denote this notation. We have this notation, x ordered 1, we say that is the first order statistic. This is the smallest observation, and the second smallest would be this, and likewise it can go up till the maximum one, which will be x ordered n. So likewise it will be true in this case also. Now when you look over here, that theta is greater than x ordered n, theta is also greater than x ordered 2, theta is also greater than x ordered 1. It suffices to say that theta is greater than x ordered n, because if theta is greater than the largest observation, then it is definitely going to be greater than all the rest of the observations. Theta is going to be greater than x2 also or x1 also, right? So in this case, it suffices to just say that theta is greater than x ordered n. Okay. So if theta is greater than x ordered n, so your likelihood function in this case is just 1 over theta raised to the power n if theta is greater than equal to x ordered n. Now you need to maximize this likelihood function. Now likelihood function over here, it is a decreasing function of theta. If you look at this side, it is a decreasing function of theta, which means that maximum of this likelihood function would occur at minimum value of theta, okay, because it is a decreasing function. And what is the minimum value of theta? It is x ordered n. That is the largest order statistic. So In this case, your theta hat would be x ordered n. Okay, as opposed to the one that you obtained from method of moments, that it was twice of the sample mean. So this shows that the two methods of estimation can give you different estimators. Okay. Now also this example is important because here uniform distribution is one of the distributions in which the support of the random variable, that is you have x here, the parameter is involved in this case theta, right? Parameter is coming in the support of the random variable. So it means that if you cannot just skip this part and do your likelihood estimation with just 1 over theta, right? You cannot differentiate, you cannot take log and differentiate, and those things are not possible because essentially you would be skipping this part, right? And you cannot miss it because here the parameter is still present. And if you solve this by just differentiating and so on, obviously the result that you get would not be correct because you have this also present. Unlike if you see the Bernoulli case, why did we take the likelihood function, we calculated this, and then we took the log and differentiated it. So that is the usual procedure of finding out the MLE. But here if you see, the support of this is 0 and 1, right? So this is independent of the parameter p over here. So that is why it will make sense to consider these steps. However, whenever in the situations where you have the parameter present in the support of the random variable, then you should be careful in not skipping that part and instead incorporating it to find the answer. In this case, because likelihood function over here, it is a decreasing function of theta, so maximum would occur at basically the minimum value of theta, which is x ordered n. So now we come to the fourth part, which is, so our fourth example corresponds to normal distribution with mean, mu and variance sigma square. So in that case, what we obtained was, in method of moments, our parameters, the estimators that you obtained in that case was x bar and n minus 1 over n s square. So let us see if we get the same estimator when we use the method of maximum likelihood. Okay. In this case, what is the PDF of normal distribution? As you all know, it is 1 over sigma root 2 pi e to the power minus 1 by 2 x minus mu by sigma whole square, where x from minus infinity to infinity, mu is also in R and sigma is greater than 0. Right? Now if I have to take the likelihood function with respect to the parameters mu and sigma square, so what will be the likelihood function? Product I 1 to n. So 1 over sigma root 2 pi would be there, e raised to the power minus 1 by 2, it would be xi minus mu by sigma whole square, right? You can simplify this since there are n such terms, so it means it would be, I could also write this as 2 pi sigma square raised to the power minus n by 2, okay, because this is basically what, sigma root 2 pi to the power n, right? So in this case it is 2 pi raised to the power n by 2, and here it is just sigma raised to the power n. But since we have to find the estimator for sigma square, it makes sense, and it is also better that if we try to write this as sigma square raised to the power n by 2. Then the differentiation, because when we are taking the log and differentiating it, it would be with respect to the parameter sigma square. Had it been, if your interest would have been in the standard deviation, that is sigma, then you would be differentiating it with respect to sigma, and probably this, keeping this as sigma raised to power n would have made sense. But in this case, we are considering variance, so here it would be 2 pi this step, okay. And if you take in the numerator, it would become minus n by 2. And what do you have over here is e power minus 1 by 2 sigma square summation xi minus mu whole square. Okay. Now I can take the log of this. So it would be minus n by 2 log 2 pi minus n by 2 log sigma square minus 1 by 2 sigma square. Sorry, there would be no log now. So minus 1 by 2 sigma square summation xi minus mu whole square. Okay. So this is the log of the likelihood function that we have obtained. Now first let us differentiate it with respect to mu. Okay. When we differentiate it with respect to mu, what will you get? So the first two terms won't contribute because there is no such term for mu. So this one would be, so you have minus 1 by 2 sigma square. So this one would be twice summation xi minus mu, but here 1 minus would also come because mu is negative. So and 2 will cancel out. So you will have summation xi minus mu by sigma square. Right? When you equate it to 0, basically over here, suppose summation xi minus mu over sigma square, this is equal to 0. This is equal to saying that summation xi minus n mu would be 0, right? Because summation, when you take inside for n such mu, it will be n mu. And from here, you see that mu hat is nothing but summation xi by n, which is your x bar. So the sample mean that you have obtained is going to be the estimator for the population mean, x bar. Okay. So for mu hat you have obtained. Now you have to also differentiate it with respect to sigma square. So let us see what will you get. So del by this sigma square. So you see that we are differentiating with respect to sigma square because your interest is in finding the estimator for sigma square. Okay, as I just mentioned earlier also. So be careful with this, with what is your parameter of interest. So in this case, if you see, so the first term will obviously not contribute. You will have just this term. So minus n by 2 log sigma square and the other one. So let us write that. Okay. So from the first one, it is minus n over 2 sigma square plus you will have the other term as, let us see what it is, minus 1 by 2. So this one would, summation xi minus mu square would be the same. And here it will be plus 1 by 2 sigma raised to the power 4 because you are differentiating with respect to sigma square. So that is why it would come and summation xi minus mu whole square would come. Now you can equate it to 0 and you will see that what is your answer. So when you equate it to 0, let us see what you get. So here it would be, when you equate this to 0, it would be 1 over sigma square. Okay. Sigma square would cancel out. Summation xi minus, sorry, instead of mu you would be substituting here because you have already estimated mu, right? It is x bar. So here it would be instead x bar over here. The parameter, if we have estimated the first one, you will be substituting that in the second case because you will not be writing the population parameter because again you don't have anything to do with it. Xi minus x bar whole square, this would be n, right? Because sigma square would cancel out, 2 would cancel out. So you will have this, and here if you have to find sigma hat square, so it would be 1 over n summation xi minus x bar whole square. Again, if you can recall, the numerator is basically, if you see, right, in terms of sigma hat, in terms of MLE estimator, it would be n minus 1 times of s square, sample variance. Okay. So what you have obtained is that for mu hat, or you can say that your mu and sigma square, the MLE for this mu and sigma square is jointly x bar over n minus 1 times sample variance time divided by n. Okay, so we have considered MLEs for 4 different distributions. First 2 were the discrete case, okay, binomial and Bernoulli family, and then we considered for uniform, and we saw that in uniform you get different estimators, and for normal you see that both the methods give you the same estimator. Okay, either you use method of moments or your MLE.